I know a few of you, and I see a lot of new faces, so this is the perfect ratio for me. I have my comfort colleagues here, and then a lot of new people to connect with and to meet today. So thanks for coming, and thank you both for having me here. I really appreciate it. I haven't been in this building ever, so I never had the opportunity. So I was asked to talk about big data and how they meet with our artificial intelligence work and how we bring those together to generate science and conservation outcomes. How do you talk about data in a fun, interesting way? How do you talk about artificial intelligence in a fun, not scary way? I think you do it by showing a few examples of how we've used it. I know a whole lot about both areas. I originally, as Amanda said, I started here on Molokai Island working for TNC in 1992. And I was tasked with working up in Kamako Preserve and finding both invasive species and also rare and endemic species for special treatment, special ecological protection. And I quickly found out that it was an impossible task. And I decided to go to grad school to put off the task. And here we are 25, 26 years later, and there are aspects of this that we have cracked and that we know how to do better than we did back then. So there's been forward scientific progress. At the same time, we made a lot of discoveries in our efforts in Hawaii that have to do with bigger issues than just Hawaii, meaning global carbon cycle, global climate change, and different aspects that I'm going to talk about today. All of those have been driven and made possible by the confluence of big data, and I'll talk about big data, and really the rise of AI approaches. And so in my group, if you come to my lab, I have about 30 people in my lab. About a third are hardcore ecologists who are in the field. About a third are remote sensing, mapping specialists, and about a third are AI people nowadays. And these are data scientists, that's the term that's used. They're agnostic to task in general, but they know how to get people like me from A to B in ways that I never thought were possible when I was a grad student or even as a young faculty member at the Carnegie Institution for Science. So that's my talk. I'm losing my voice already. What drives us? I could spend 15 minutes saying what drives us, but I bet you we all agree on certain aspects of what drives these needs for conservation and science to go up a notch. And I just put it in this one slide, rather artistic rendition of the trade-offs between climate change, and you see the CO2 here coming off of this, the destruction of ecosystems, or the three-pronged trade-off that I place all of my work within, and also try to generate that conversation both within and outside the science community. I want to mention something about my program, and then I'll go on to the talk. I've had this lab for 18 years in its current configuration, and let me tell you, they are an amazing group. They work in private sector, they work in the spooky part of the federal government. They've gone and done all kinds of things, but really what this lab has done is combine science and technology to really understand what we can do better. It says biologically rich places. I think we've done more than that, but that's been where our hearts have been. So Hawaii has been a key place because of its high levels of endemism and its uniqueness. I'll talk more about that. I won't go through this because you have it in front of you. It's just a reminder to me to tell you that all of that 20 years ultimately led to the opportunity to take my program from the Carnegie Institution based at Stanford with my lab on the Big Island to Arizona. There's an amazing set of opportunities that ASU has generated under President Michael Crow. I've been challenged and also gifted the opportunity to generate a new center, which is in day 3. So I've been working on it for about 18 months quietly. The center is called the Center, it has a lofty name, Global Discovery and Conservation Science, because my world has been grown, my scientific world has been grown on the idea that we can make discoveries and have conservation outcomes simultaneously. Not one after the other, but actually in real time. And we've done that all around the world, especially including in Hawaii. These programs that are listed here are my ideas. Some of them are very mature. The one that's based on the Big Island is the Pacific Ridge to Reef program. It finally got a proper name a while back. It's really in its 20th year. That's how long I've been this global discovery and conservation science with new resources that ASU is bringing to bear to help us grow it. And I'm going to talk a lot about that one because we're here. But I didn't want to leave out the other ones. You'll see we have a strong AI component. Again, that's a team that will be growing in the center in Tempe, Arizona, but also in Hawaii and elsewhere, that are the AI specialists that are helping people like me, maybe like you, to do what you thought was impossible because the AI technology is moving so rapidly and in expansive ways. I'm going to talk about the Carnegie Airborne Observatory. That's my airborne observatory that I invented in 2005. It's now being rebranded as the Global Airborne Observatory because we are also expanding that. So although we're going to Earth orbit through companies like Planet, which I have a deep role in at that company, we're also still understanding that we have a lot to do at the airborne or the aircraft level. We're also looking at how science can work directly with journalism to generate more integrative outputs in terms of transparency, and also helping you scientists get your word out better. If you know my work, I'm into generating your story. And I think that's really important, especially given the way that life has been in the US the last couple of years. So Manga Bay News Lab is our integration with the monster environmental reporting organization called Manga Bay to generate that opportunity. And you can read these, but I'm just narrating over the app on it all. That's the one where we bring together people to create opportunities to use technology to come up with new conservation strategies, outcomes, and opportunities. I just did this just in case I needed to do it. Why Hawaii? Why base here? And a lot of it has to do with the uniqueness of the biology of Hawaii. The second part is that the ecology of the system is amazing to us, people like Creighton, people who are in this room. The system is has a global range of environmental conditions. I think 23 of the 30 or so Holdridge life zones are found in Hawaii, many of them on the Big Island, but across the state. Some of the wettest and driest places on Earth and so forth. That gives us this laboratory to develop not just the science and the conservation opportunities in Hawaii, but to have some sort of model system for the larger planetary challenges. And many of us in this room, my group has used that model for a couple of decades. Societally, we also have the same. We have some of the poorest folks on the planet to some of the wealthiest. We have all kinds of demographic variation, all embedded in this same bioecological zone, or socioecological system. And that gives us yet more dimensionality in understanding how we can generate positive conservation and human livelihood outcomes using science and technology. And then the technology component has been a major part for us here. If we were trying to develop this, I worked a lot in the Amazon basin. For those who know me, I've worked there heavily for nearly 15 years. You wouldn't be able to develop the kind of technologies that we have there because those rainforests and those environments are they're just not developed enough to actually have a place to do technology innovation. Hawaii is just the right balance where you can get access to, whether it's internet or big data pipes or whatever it is to actually get moving along. The Carnegie Airborne Observatory is what we do. It's about 10% of what we do, but it's allowed 10%. It started out, all of it was conceived, developed in Hilo at the Hilo International Airport, which I'm not sure it's international, but that's what it's called. It started out in the back of this Piper Navajo in 2005, and this is after 7 or 8 years of NASA-funded research. I decided that NASA's support was invaluable in my training and my upbringing in terms of using high-tech methods for conservation, but they aren't built for conservation. So I developed this new idea that we would build our own airborne observatory, started out in this hunk of clunk, flew it around haphazardly, got it done, graduated up to a Twin Otter by 2007, graduated up to this Dornier 228, 212. This is the 2015 launch of it shown on the right. It's a very neat airplane. It's sitting at Hilo Airport. Actually, it's in the air today over the Mauka side of the Kona, on the Kona Forest, up Mauka on the west side of Hawaii. We're remapping the rapid Ohia death, which I'll touch on momentarily. It's a high-tech laboratory. You are welcome to come out. The plane is in Hilo about half of every year. When it's not in Hilo, it's in maintenance on the mainland, or it's deployed overseas. Our most recent one was we mapped the northern tip of Borneo as an example. And we did the Caribbean coral reefs just after that. So that's the airborne lab. These are the ingredients of generating big data. This lab generates 2 terabytes of raw data per flight. 2 terabytes of raw data per flight. Why? Because it has 5 instruments on board, very powerful lasers that fire out of the bottom of the plane and image the forest in 3D. I'll show you that. Imaging spectrometers that measure chemistry and species and the things that we have put out over the years. Other high-resolution cameras, and then other data streams. And so you generate 2 terabytes a day, you fly for a month, you can do the math, and then through that hump of 2 terabytes per day, out to about 6 terabytes of processing, and then collapse it to megabytes of product. And how do you do that? So we've had to generate both computing-based innovations. We used to talk about processing on CPUs. That doesn't occur in my world anymore. We left that behind nearly 4 years ago. We only process on what are called GPUs, graphics processing units, or graphic processor units. They are much, much faster and have better thermal properties for really running high-speed calculations. And so GPUs are really what we do. And actually, those are going to go away. And 2 years from now or less, we're going to be onto a whole new technology. I won't pretend that I know the names of the details of those processors, because I don't. That's what my team does. But that's where the hardware is going. ASU has a big investment in that, and that was another draw. I could use that investment. And they're looking for collaborations. I just heard the other day that ASU is generating a multi-state collaboration with this GPU technology to allow for super high-end processing in the cloud. But this is the kind of machine that generates the need for that. What are some of the outcomes of taking big data with, say, an aircraft system and then using AI approaches? I won't bother you with the details of AI, but if you are an AI person, the thing we do the most is something called convolutional neural networks, CNNs. Not the news station, CNNs, convolutional neural networks, and also other things called support vector machines and gradient boosting machines, and all these special names. They all have to do with the ability to recognize objects, both spatially in image data, but also their behavior temporally, if you have multi-temporal data. And third, their properties, meaning if the measurement has, say, a spectral signature, we can generate the ability to extract information about, say, this table, what its chemical composition is. So we have space, time, and its composition. And that's what AI does. And it's the same stuff that freaks you out when you go on Google Photos and it says there are the photos of you, and there's your aunt, and there's your uncle. And that's all the same stuff. And when I was a graduate student, for you students here, we had neural networks. It's just that the computing wasn't available yet, quite yet. And some of the constructs were AI background without boring you to death about how it works and the details. But I'm happy to answer questions about it. Some of the approaches used have been, for example, one of the grad students that I had used it to map out, with colleagues, use it to map out certain critically important invasive species. This one is probably Falcateria mollicana, the albizia tree. That's a pretty easy one. Some of the hardest ones have been looking for these trees that are likely infected by this thing called rapid Ohia death. Who's heard of ROD? Yeah, so I'm going to show you some ROD results. It's all AI and big data based. Oh, I'll show them to you now. This is one of my staff members, Nick Vaughn's work. Brilliant data scientist / forest ecologist. He's used, this is a lot here, but he's used the high-tech measurements from the Airborne Observatory, and the 2 measurements that are critical are the lasers that measure 3D structure of the trees, and secondly, the spectrometers that measure the chemical composition of the leaves in the trees. And using this is the AI. support vector machines and gradient boosting models to actually detect where these trees are likely to be that have the rod pathogen. The pathogen is Ceratocystis, two species in that genus called Ceratocystis. It was introduced, what is it, how many years ago now? 7, 6, something like that. Yeah, 7 or 6 years ago. One of its expressions is the browning of the leaves in the trees, and you see that here in this, if you squint, you can see those here. What we found through field work that we did with the US Forest Service and the USDA, so the AI, the spectroscopy isn't seeing the fungus inside the leaves, but it's seeing the expression of the fungus with that kind of repeatability. This is, you'll have to stare at this as I flicker between two data sets. This is 2017 that's been out for a while. In 2017, there are 43,000 new tree crowns that had the suspected rod fungus. In 2018, no one's seen this yet. I think you're the first group besides our DOFAL and DLNR collaborators who are funding this. 46,000 new ones. So this is new. This is the production of new rod ohia trees. And if I flicker, this is the 2017 coverage. In 2018, I'll show you, we did not fly Lower Puna. Not because of the volcano, but because it had taken such a course, we decided to spend more time and money flying the big island in Maui. So we had to cut something out, just in terms of time and money. But you can see the difference in the areas of overlap. 2017, 18, 17, 18, 17, 18. So, and unfortunately, a JPEG makes these look like it's everywhere, but if you zoom in, they're dotted and spaced out. So it's not that bad. But it has increased quite a lot. And so that kind of measurement is not possible from satellite. It's not possible at these scales from drones. It's just right for an aircraft type program that uses high-tech measurements with AI to find these brown trees in a sea of millions of live green-gray trees. Another example from the Hawaii Pacific Ridge to Reef program is our carbon research. It started on the Big Island, it went to all islands, and then it went global. And this is the deeper story. The deeper story is we've been challenged for many years with trying to get a grip on some of these fluxes, carbon fluxes as we call them. We have this about 9 billion tons of carbon coming out from fossil fuel, cement, and other human activities. We have another major gross flux from land use change, mostly deforestation and fire-related and fires. And then we have these sinks. The ocean is a natural sink. There are land sinks, and so forth. So we've been, for a long time, we focused on getting this part of the puzzle figured out. Other people were working on this big elephant in the room, which is our emissions. We were going to work on this 1 petagram addition, which turns out to be quite substantial in terms of global warming, its contribution to global warming. To give you an idea of how big this stuff can be, this is one quick snapshot I took from the cockpit of our plane doing the Amazon basin. We spent years down there because they needed high-resolution carbon maps before this would happen so they could calculate how much carbon is literally in these fires. It was poorly known, plus or minus 100% error, it seemed, at the time, which means 0 to 200 tons per hectare. And so we spent a lot of time figuring that out. The idea behind all this, and this was ultimately funded by private philanthropy in Hawaii and then by Norway and UN Development Program and others outside of the Hawaii, was to come up with measurement approaches that would support the ability to provide incentives for sequestering carbon in forests. That's what that says. For years, we had been doing satellite-based forest cover mapping, and it's gotten way better over the years. When I was a grad student, a single Landsat image was like, I think, $2,200 and hard to analyze. We didn't have the computers or the software to do it. Nowadays, we can do that quite well, and there are online systems to do that. That's the 2D cover of forest, two-dimensional cover. What we want to do is get to the 3D, which is the one that you really need to get to the carbon estimation. We developed, starting in 2001, with other people's hardware, but with our own hardware in 2005, high-tech laser scanners that are now commonplace, and that's a good sign, that allow us to fly over, sorry that this is washed out, but to image the forest in 3D by firing lasers out of the bottom of the plane. When you get a really high-end LiDAR built, like the ones we build, it's not commercial LiDARs, these are Carnegie LiDARs, you can image the system from 8,000 feet and get a detailed look of the 3D canopy as you fly over, digitally fly over. And from those data, you get the volumes of these trees. And then you apply a series of field-based studies about wood density so that you can get the actual biomass. And that science of field and airborne technology, that's a science of fusing them, has matured wildly over the last decade to the point where it's operational. This was covered in 2011 in Nat Geo. This is a look at a forested area that had just been taken out by a new road that was built in the Amazon basin. High biomass trees are in red, or tall canopy. Shorter canopy in green, and then the deforested zone. And one of the critical things of being able to do this, critical outcomes, is that it isn't a simple map. It's very complex in 3D. It's not just forest cover, but this area has secondary regrowth, and other areas have been selectively logged. And so in 3D, that forest is highly complex, and it was complexity that we were not seeing from space very well. That was why they covered this in Nat Geo. All of that idea for us was born on the Big Island with this jalopy of an airplane that I told you about. And then it's finally we got into a Twin Otter, a larger aircraft before the big one that I have now. And what we did was we spent years testing and retesting, flying and reflying forests of Hawaii Island to try to figure out not just how to do the carbon mapping, but if we could understand the relative importance of, say, ecological processes and human activities in generating the landscape of carbon. And this is above ground forest carbon in this case. And you can see the different levels shown here. This is 2011 technology. By 20-something, we did the whole state. And we did that through a new approach because the aircraft is too expensive to fly everywhere all the time. So we use sampling with the aircraft combined with a series of different satellite data sources and an AI approach, where what we're doing with the AI in that case is we're using the satellites to detect changes in pattern in the forest, and then using the lasers from the airplane to say, what are the carbon stocks of those changing patterns? And the AI gives us that relationship in a way that, say, regression and the old methods that I was raised on don't really work. And so the AI approaches, especially in this case, something called random forest regression trees, or nowadays that we use these things called CNNs, convolutional neural networks, allowed this relationship between the aircraft sampling and the satellite data to generate this statewide carbon estimate with very good precision and accuracy. And we did the whole thing for about $200,000. So that was the breakthrough, was the money breakthrough, because everyone said the planes are too expensive, we can't do it. Once we did it for $200,000, we were able to do it per hectare for 1 penny a hectare because we got better and better at it. And then the government of Peru came to us and said, please map our carbon. We did it. Red is high carbon, blue is low carbon. That's a deforested area of Pucallpa if you've ever been to Peru. Here are the Andes. It gets dry on the leeward side. Being in Hawaii, you guys understand that. So there is very little carbon on one side of the country. Panama did the same thing. This was UN FAO brought us in with the Smithsonian, said, please map the carbon. Here's the Panama Canal Zone. You can see forests that are maintained just along the canal. A lot of deforestation in that country. And we've gone on, and now the approach has been used in 137 countries. And that's an example of how Hawaii-born science technology, using Hawaii as a model system, generating some of our knowledge that way, and then building it out from there, has led to, I just circulated yesterday on Twitter, even a new update on how this global carbon mapping can work at high resolution.
Is that real? There's Southeast Asia showing high carbon.
It's real at the time. That's a 2014 map. So you're looking, where are you looking here?
Yeah, the whole area.
Yeah.
There's an awful lot of green there.
Yeah. Borneo then, yeah, Borneo has a lot. We've been to Borneo with the plane to verify, and it was some of the highest we ever had. Some other things about Hawaii that are interesting that have used the AI approaches, spatial convolutional neural networks allow us, for example, to fly over these prehistoric Hawaiian ag fields in Kohala called the Kohala Field System up here, and generate detections of where these walls are below the grassy surface. If you're out there, you can see them. If you're with someone like Peter Vitusik, he'll put you down the line and say, there it is. And you go, there it is. But a lot of these are hard to see. So the spatial artificial intelligence approaches are looking for linear features in really subtle 3D LiDAR data or laser data. And this is just a small section of them. And from that, we were able to map with the archaeological colleagues that led this, we were the support team, where the different densities of these walls were. And those folks used that to interpret not only the prehistoric extent of these walls used for ag, but also by the spacing of those walls to infer differences in resource regimes at the time that those walls were built. Walls spaced closer together were in, I think it was drier times than walls that are spaced more widely apart in terms of capturing leeward rainfall in Kohala Mountain. So there's really neat approaches that use 3D data in this case, but with the AI approach to detect these walls. In 2015, I've been kind of a closet marine ecologist for a long, long time. I actually started there before I went to land. Not as an ecologist, but for love for the sea. But the 2015 bleaching event that we all encountered here, who was in that one with us? Notice the hot water temperatures. Generated a need for us to try to use some of these same approaches in the sea. And this is a wrap-up of everything I'm about to say. Here's what it was like on the Big Island, a place that I learned to dive, not learn to dive, but learn to appreciate coral reefs 30 plus years ago. We started seeing hot water affecting, especially, for example, this species known as Passalopera. And then big Parietes lobatas started bleaching. And then, sorry, a little rough on the big screen. But then by the end or late in the bleaching event, you had just these stragglers of living coral shown in the bright colors against this massive sea of dead coral that occurred all in about 8 weeks, maybe 10 weeks if you round up. It happened fast, and that's the new regime that Hawaii is in. It's the regime that you're seeing in the news all the time. One of the big problems is, how do you manage that? Is there anything you can do to manage the system in this case? And that's where a lot of our work has been. The science and technology side, we had to solve a bunch of problems all at once. The big data problem, the AI issue, and the mapping and interpretation issue. And this is just a cartoon of all the different characteristics of the sea surface and what's called the benthic surface or the reef surface. We had to figure out the physics of with our particular instruments. To do that, we did crazy stuff. Robin and I and colleagues, we went to Home Depot. We bought roofing tile, roofing panels, and put them on the seafloor. If DAR is in here, we took them out. They're not there anymore. And at different water depths and in different conditions, here's a blue, green, white, and red, and flew over them. And here's our boat, and there they are, and flew over them and figured out the physics of this flying over Home Depot roofing panels. Okay, and that took a lot of work just to figure out how to map the seafloor in more detail than we ever have before. This is the outcome of that. It's a little cut off, my apologies. But you get the idea that that's Ho'onaunau Bay on the Big Island. There's the City of Refuge. There's those few houses. Two-step, if you ever snorkel, is right there. It's a 3D image. It's about a 1-second collect with our airborne observatory. You see the 3D on land, and you get a sense of, we are now mapping routinely to 17 meters or 55 feet of water depth in terms of 3D, super high resolution at 40 centimeter resolution and its rugosity, its 3D structure. And then critically, the spectrometers have allowed us to assess what's on the seafloor. This is brand new stuff. I haven't even published this yet. Probably something I'll do this year. These different colors are, yes, are live and dead coral mixtures. The L's are good, the F's are bad. I could take you through these, but this is Honaunau Bay, and what you see is that it is not a uniform benthic surface. It is highly heterogeneous. If you were to go out there and swim, and those of you who swim a lot would probably agree that these are pretty big swims to do. Depending on where you get in the water, you're going to get a completely different view of what's going on. And that's the problem right now with reef mapping, is that it's so biased to where you get in the water that we really wanted to develop a method that will get us to this geography of what's in the water or what's on the seafloor. This is benthic microalgae. This is filamentous algae on dead coral. This is live mound coral, live plate coral, live finger coral, and so forth. Here's another view. Since it's 3D in the lab, you can turn it in different ways and see it and explore it. And you don't have to be a diver, because in my team, we only have 6 instructor level divers and tech divers, and the rest are AI specialists that need to actually do this work. So we give them this, and they're in there in the lab doing this in 3D and trying to understand the relative amounts of different surfaces, different ecological surfaces. Another thing we've been doing with the same approach is finding the survivors, the refugia. Where are the corals that survived the 2015 event? Do they have a relationship with the land? Do they have the relationship with something else, like overuse, fishing, whatever? We don't even know that. So we use the same approach. This is Honaunau, just to keep it simple. Now the land is removed and the water is removed, and now you see the coral reef system, a little grainy on the screen. You get the idea. And here are the detections of the mound coral in the genus Porites, for those who are interested. And so those are the survivors. Higher density of survivors on the south side of this bay than in the north side in general. But we don't even know the controls over this. These are the first maps of this ever. We did, at the time, the full west coast of the Big Island, right, not long after the bleaching event. And this is just a reduction of a lot of complexity. Remember I said we started 2 terabytes a day? To map this coastline was something like 20 terabytes of raw data, jump up to 100 terabytes of processing data, boom, down to 3 megabytes of a GIS layer. And that GIS layer is what I want. And I want to have that so I can interact with the management and conservation communities and so forth. And these different bars show the relative, the relative bleakness of what was out there. Blue is relatively good, red are terrible zones of massive mortality. And you can just see that. And one of the discoveries, it's not really a discovery, one of the confirmations that we're getting is that areas where there's a lot of groundwater outflow, cool water coming out of the mountain, is where there were relatively higher survivorship of corals and lower amounts of turfing, which is shown here. Turfing is this thick algal cover that occurs after a coral dies. And it's in one bay, it's just a small amount of suppression. This is good in the embayment. This is worse outside of the embayment. The embayment is where cool water is coming in. And you can see it in thermal imagery, for example, in Honokohau Harbor. After I found this, I didn't have a thermal sensor on board, so I built in a very high-end sea surface temperature mapping system in our aircraft. It's also mapping at 40 centimeter resolution. So I don't have the data to show you today, but all of those benthic data are now being fused with the thermal data so we can really get a grip on this. This is my last slide, I think. Going forward in Hawaii in the Pacific Ridge to Reef program, which is part of the Global Discovery and Conservation Science program, which is at the Arizona State University, really working on integrating land and sea, and that's where I think everybody in the room, whether you're into reefs or into land processes, social science or natural science, I think that's where the rubber's going to meet the road in trying to understand how sustainability science can move forward in a place like Hawaii, but anywhere really. Hawaii is the great system, the model for looking at this. I'm really strong believer of that. So I think that's where we're going. This is Hilo. It may not be the hub of the planet and the universe, but it sure is a great place where we can connect these issues both from highly, relatively developed areas to areas that are still, frontier type country. I just want to say that if you're interested in any of these cross-cutting disciplinary areas, I am really intent on growing each one of them. I gave you kind of the Hawaii part of the story out of this. This is a global story. and we're looking for people. I also will put a plug in for postdocs who might be in the room that I have the green light to hire probably around 6 new faculty, and your labs can be part of this. Also, we have opportunities for graduate students and postdocs galore, and we're very interested in the interactions with East-West Center and the University of Hawaii system and so forth. So I'll leave it there and answer questions.
Fantastic.
Sorry for the bad voice today.
Brilliant job. We actually have 20 minutes for questions, which is very unusual.
Ooh.
Thank you for being so disciplined.
Yeah. Or I just didn't have more to say.
I have plenty of questions. If nobody wants to kick off, fantastic. I wanted to ask about the carbon piece, and I apologize to those brilliant scientists in the room for anything silly I may say, but trying to understand about the role that soil sequestration plays in carbon. I get the forest piece. How do we figure out soil sequestration, and how do we figure out also the role of the oceans, and as the oceans warm, what some of the risks there might be?
Okay, soil carbon in my world is normally done using a model. So we might take spatial data from satellites or aircraft or GIS data that have been put together by people from the field, compile those in to constrain what would ultimately be a simulation. It could be a simulation or even just a correlation with soil carbon stocks. That's how that's done spatially. One of the cool things about soil carbon, I did a lot of this soil carbon mapping, especially in outside of Hawaii, all over the place. We found that you can have a deforestation event and the soil carbon will start to leak out at that point, but it's not like it's all gone unless you've tilled it. It's a slow leak. Soil carbon is slow in and slow out, compared to forest carbon, which is slow in and fast out because you chopped it down. So for example, in Brazil, we worked deeply with the Brazilians to figure out how long a forest had to be left alone to regrow naturally before that soil carbon would start to leak out to the atmosphere. And that was done using models and field measurements combined with satellite data. Satellites and aircraft do not see soil carbon directly, only the correlates.
So how do you figure out if you've got, say, big plantations, which are not the kind of regenerative processes? How do you figure out if a big plantation, as opposed to smallholder farmers that might be employing sustainable methods, how does the model simulate?
Correlative. It's going to be correlation there. That kind of thing I've been involved in. I have been involved in multiple projects over the years where you take a landscape of smallholders and large land, tenured people who have tenure on that land or are working those lands, and get out there and get the soil carbon measurements and get the relationship with what can be measured from above. For example, tillage. If the system is being left, do you know what till and no-till is? Like. Help me out. Plowed and, thank you. I'm just losing my words. Plowed and unplowed, yeah. That kind of thing has a big effect, and it's measurable from aircraft and to some degree from satellite nowadays.
Fantastic.
And there are other things. There's a longer answer, but those are some tidbits.
And then I'll let other people. So if you're thinking about Africa having 60% of the world's arable land, of which only 2% is used, and the African Development Bank right now is thinking about how they pull Africa out of poverty through agricultural projects. And they're saying, well, really we think we have to go the big traditional monocropping route, because if we do smallholders, it's not going to be fast enough for... So what messages might there be for them to look at as they're thinking about the climate dimension of their poverty planning?
So do you mean, I have to answer the question with a question maybe.
Okay.
Do you mean under conditions of, say, increasing drought or hot drought, will their practices need to change in terms of keeping more carbon in the system?
No, I'm meaning that right now we know that Africa has an estimated 60% of the world's arable land, but only 2% of that is being used. So the African Development Bank right now is working on a strategy for agriculture, and they are saying to pull people out of poverty, we really need to go the traditional US monocropping, which I presume would involve tractors and tilling and all the rest of it, because the smallholder cooperative model, which has been proposed, we don't think is going to work for poverty. But is there a message there for them around the carbon dimension of what they're planning that they should be taking into account if they're looking at this holistically?
I don't know that the incentives are strong enough yet for them. That's really what I worked in Cameroon for a couple of years with now Dr. Elsa Ordway, who's at Harvard. She was a grad student of mine and Eric Lambens, and putting oil palm development against soils or carbon sequestration in general is a pretty tough sell when the country is trying to grow, right? Yeah, I mean that is the issue. So I don't have a good answer right now.
Okay.
Yeah. That's why it's coming from Paris Accord thinking, and rather than from bottom up there.
And then McKenna, Jack, and then we'll come around here.
Hi, I'm McKenna Kaufman.
Hi.
I think this is really interesting work, and I'm wondering if the methods that you've developed, in the 130 some country mapping you've done, what are the uses, or are they being used in developing accreditation, for carbon offset market?
Yeah, thank you. The answer is everything under the sun I've seen with the data now. It's pretty mind-blowing. I've seen good, bad, and ugly, the data used for all things. In some countries, I'm seeing it used. Colombia, I'm just trying to think of one that I like to talk about. Colombia, when we did the carbon mapping of Colombia, and it was just before the peace accord was written with the FARC, the rebels of Colombia. The worry was that a lot of big business was going to go in there and remove a lot of carbon, so they were going to get it measured ahead of time and then use that as to incentivize protection with business as it came in. I've seen it go both ways in Colombia. I've seen the data used to do what it was intended to do, as I just said, and then sometimes companies have come in and said, well, there are some lower carbon areas that we're going to take, and they happen to be way more extensive. So actually the net emissions were higher than if they had just taken a smaller high carbon forest. So I've seen kind of everything done with this. I've also seen, what else? A lot of private businesses have come in. Airbus came in to Madagascar and did a bunch of voluntary, I don't know what my problem is today. Voluntary carbon investments in Madagascar because we mapped the carbon and showed that it was worth investing in. So Airbus just came in privately. I mean, I can give you every answer that you can think of probably. I probably have a place that fits any of these. The problem is that we don't have a system globally yet. One of the other problems might be, but I think the problem is social science and political science and not natural science and remote sensing. But one of the problems I should mention is that this forest carbon mapping capability was airborne only until recently. And it made for even though we went around and did all these countries, it made the repeatability extremely low. And that's made it hard to generate a blanket plan that can work, say, in the Paris Accord, but that's radically changing. If anybody knows about JEDI, does anyone know about JEDI? Hey, Kim. So JEDI is a new mission that's on the space station that's going to measure forest carbon globally. And it was just launched in the last week of November, and it's up now. And so, the scalability of the science is actually ahead of some of the political science scalability, and that's why I think I don't have a good answer. Another thing that I've noticed is that supply chain issues are still a big unknown, hard to track, and makes a lot of the traceability of the carbon very hard to get our hands around, whether it's private, voluntary stuff, or government, or international. So I still feel like we're in the early days here.
Thank you.
Yeah.
Thanks for a great.
Hey, Jack.
That was incredible. My question is actually kind of related to McKenna's, and we have a statewide goal to go 100% renewable here, and we have a new policy to be carbon neutral by 2040 or 2045 in our Hawaii green growth targets. So I guess my question is, could you determine how much of our carbon problem locally we can fix through reforestation with your forest carbon mapping? Is it 20% or 30% or 50% of our issues? Because obviously there'll be a lot of biodiversity benefits to reforestation, but we're also fixing our carbon sequestration problems. And
Who wants to do it? The data 100% exists to do the calculation right now. Yeah. Yeah, the data 100% exists to do that calculation. Hawaii could be California, got to California is, wants to be first. So if you notice, we fly a lot in California because Governor Brown, hopefully the new governor is the same way, wants to be the first. So yeah, it's ready.
From the Nature Conservancy, is Jason here?
I am.
Jason, fantastic. Because you guys have a project with Hawaiian Airlines to measure carbon sequestration as an offset, right? On the Big Island. Do you want to?
We haven't really finalized that yet or advertised it really.
Erase your minds now.
But it is something that they're looking at in the works for as
So
a
this
pilot.
could be useful in terms of the measurement piece.
Right.
And technically it's possible. I guess that's my message to you and your folks is it's absolutely not research. Sure, there are ways to improve things to 5%, 10% here and there. But compared to, I used to say compared to the stock market, but it's so easy now, that bar is too low. But it's really well measured and is technically not this crazy mountain to climb anymore.
Right.
Yeah. Yeah, let's, one, two, go ahead.
Hi, my name's Kristen Reynolds. I started out in engineering and data, but then moved to the policy world because I was frustrated that data didn't change people's minds.
Right.
So I was just curious your experience of how you've used kind of storytelling, or
Yeah.
have you gotten people to come on your side or do they just use your data for their story? Different story.
Kind of like the earlier question, I've seen it all.
Yeah.
I'm super calloused because of it all. I smile. But, and I am positive. I really am positive. I don't have to put on a fake positive here. There's been some amazing progress. Not just the science, I mean using the science. People say, why does, for us, and like Kim works in Indonesia, people work in different subregions because I think the deeper investment is that you're the science, that science is only going to have that impact if the scientists are there integrating, not leading, but really integrating it, right? And I think we all know that, and I just want to say to people who are new to the field, do that. Find your region or a few regions and make that investment and generate that outcome. In Peru, that's where I spent a lot of time. I was torn from Hawaii to Peru forever. And I disappeared from Hawaii for like 5 years, I think, because of it all. Basically disappeared except for Christmas and other secret returns home, right? But Peru, the government, we got them at the right time, the right place. They started the Ministry of Environment. We were contracted to be their science arm of the new Ministry of Environment. And we embedded and we hired and we put paychecks in that ministry. I got all kinds of money coming into them to generate the mirror so that we could actually work together. And the outcome has been 2 massive new national parks. Sure, it's got problems. Sure. Gold mining, problems. All sorts of stuff in the country, but it would have been way worse. I know because I know that country. It would have been way worse if we hadn't been there. So we have to generate those investments, and I think the scientists should be rewarded for doing those investments. It's and being applied. You can do basic science in the background, but doing the applications are where we need people badly. Does that answer your question?
Definitely. Yeah.
With my pontification.
I just was curious.
Yeah. Yeah, there's a bunch. I have some negative ones too. When I was in Madagascar, there was a coup. So some stuff fails, right? But you got to be ready for those failures and just look for the successes, the gross rate of success outweighing the gross rate of failure. So that's my advice. Creighton, and then back.
Yeah, I'll ask the question and I'll give a little bit of context for it. The question is, what can we do today to prepare our students for the science of the future? And the context is, you alluded to this, when we were in grad school, this sort of stuff wasn't happening.
Yeah.
And it's happening.
I can't do any of
more,
this.
And it's the future of science. Big data is the future of science. And I'm not sure we're doing a good job of training our students today to be able to excel in that environment.
Yeah, I don't really have a grand answer, but I do know some nuts and bolts. This is what this is about to me. It's generating a space where, okay, the news stuff, if you're a journalist, yeah, they need training too in this, right? So having a portfolio of activities where people can come together and learn, because I don't think that, who's a grad student here? A couple? Don't be shy, it's cool. We wish we were you, okay? So, don't we? Yeah, I mean, you can't learn everything, so don't feel overwhelmed, but you can know about it all well enough and then find your passion within that portfolio, right? And maybe we did that. What I'm blown away by is this AI world is, some people are really scared by it. I'm just positive all the time, I guess. But I see that if we don't harness it, then it won't be used for good. So we got to steal more of those people. Is anyone here a data scientist, AI specialist? Yeah, good. Stay with us. Don't go to Google. We lived down the street from them for too long. I don't know. It's hard, but I really think that access to the technology, access to simple answers about how it works. Like, you know, I ask my guys, how does this work? And I have to ask 10 different ways. It's like a different language. Not just a language, but a thinking space. So we have to learn how to interact with those different ways of looking at this. And then I think one of the things that maybe we should all get used to is that what we know today needs to change tomorrow. I know that's cliche, but God, it's so true. And like what's in orbit today is going to be radically different than what's in orbit 2 years from now. And I know that for sure because I work with Planet very deeply, the company called Planet. So the constellation of satellites that's up there today is going to be radically different 24 months from now. Radically different. That's all I can say out loud. But those are the things that we just got to get used to and be able to interact with and not get so stuck on one way that we're not able to pick up the next way and build. What else? In the back.
Oh, thank you for your presentation. That was really great.
Cool.
So I just had a question. You talked about soil carbon and how it's really hard to map, obviously.
Yep.
For many reasons, and it's hard to know exactly how land carbon change will
Yep.
affect it. But so I've done a bunch of work in the Andes, and your map of Peru is so powerful, right? And I can see, you know, decision makers looking at that and using that for prioritization. But I'm just curious what information you do give them about soil carbon, given like the high Andes, you know, the highland grassland systems would have a lot more carbon overall.
Yep.
So I'm just curious how you balance that, right? To make sure that you're not shifting priorities away from certain ecosystems that are really important for carbon, but are harder to track and understand what the implications would be.
Well, this is why we need you. So you know, are you an ecologist? So, or biogeographer type? Yeah, so biogeography and ecology, I think, are the most important natural science field that's ever existed, of course, because I come from it. But yeah, I mean, we can map all the forest carbon we want, but we got to get the paramos, these high altitude, deep soil carbon grasslands mapped as well. And we know where those grasslands are, and then we have to get out there and get the measurements to do the correlation that I was mentioning to Amanda in a different context, right? And generate that dialogue with the Ministry of Environment and with the Forestry Department, and you know, so that because they know, but then they need to see it, right? And so they have soil carbon maps that are amalgams of all these data sets. I just didn't show it today because it's not as fun to look at it because it's a little less picturesque. But yes, but we need you. We need me, we need people to make sure that everybody understands that there's a whole system that we're looking at, not just the above ground part. That's my short answer. Yeah.
I'm just thinking it's a wonderful presentation. Where does social science fit in here? Clearly, there is a very important role. Your question is basically a social science question.
Yeah.
So this is cross-disciplinary. Where are we?
So at ASU, what happened was when I was, and I may not have the perfect answer because I'm still studying ASU. It is this beast, right? I described it as the Borg. I'm now like half connected. So what I found at ASU was that the Institute for Sustainability, which is shown here on that poster, was doing heavy social science, and I think that folks here at the East-West Center are doing that, and I think that the new Sustainability Institute at UH will be doing that, and so forth, right? What I want to do is bring a technology component to it that's really forward-thinking, that's going to support the dialogue, the interactions, and the research that goes on at the social science level. I'm not doing that in my center. These are programs that are highly technical, that are generating data feeds, knowledge, data-driven knowledge and discovery that'll support, say, management, conservation, social science, resource management, policy. The way I've done with technology in fits and spurts, around the planet, but in a more organized, structured way. So it isn't in the center, but we want you guys to come over and say, here's the problem we're facing. Can you guys work with us? Can you generate, you talking to me, can we generate, using these different techniques and different technologies, not just data, but approaches that are scalable, for example. And that's one of our major areas of emphasis is scalability of these different approaches, and allow you guys to figure out how to ingest that in the process of engagement. That's really where we are. And that's why it doesn't say there's not a strong social science piece here.
Last question from Dylan.
Yeah.
Okay, I guess a couple of slides ago you showed the infrared map.
Infrared map?
Yeah.
Mm-hmm.
It's basically measure temperature at the top few centimeters.
Of the sea surface?
So I assume you can do better, right?
Nope.
Deeper.
Not with current aircraft technology. You need to have a field component. It's like soil carbon. You find the relationships. They may not just be these 2D or 3D relationships like sea surface temperature and then the profile. We've dropped a lot of those profilers and there's not a very good relationship there. There might be better relationships with, for example, the geomorphology of the islands and thus the freshwater outflow from groundwater sources, and also embayments and their structure, their macro structure, and how water circulates along the coast and in and out of those embayments, tidal cycles and so forth. It's not that well known, even in Hawaii. Lots of research, but there isn't a place where it's all come together in a highly technical way. So I don't have that answer. But that's what this center would do, for example. Sorry.
Actually, we are interested in the opposite. We'd like to use temperature to infer groundwater move to the oceans.
Yeah, and we would like that too, because coral reefs, for example, may not see that cool water outflow. It might be too high up in the water column and although cold water sinks. So we don't know the dynamics of that well enough. And that's what this kind of center is designed to do with people. So we know the ingredients on, pieces on how to get there, but that work hasn't been done to my knowledge.
Fantastic.
Okay.
Thank you so much, Greg.
My pleasure.